Alright, I'm going to talk about the theorem that a set E contained in R is connected if and only if whenever you have a point between 2 points that are in E, that means that the third point C has to be in E always. So here I have the point. I know A is in E and I know B is in E. I'm going to draw a point here, C. And the question is C in E? And the answer is going to be yes. This theorem says that basically the only connected sets in R are intervals. But here's exactly why. I'm going to consider, E is my point in question, so I'm going to build a set around it. I'm going to let A equal negative infinity, comma, C intersect my entire set E. I don't know what E looks like, so maybe I'll just draw in. Here's E, here's E. I've got some of E over here, some. I don't know what it looks like. Actually, I know it's going to look like an interval, but I'm not pretending like I know that now because that's what I'm trying to prove. I'm going to let B. So A is equal to, A is going to equal basically all this green stuff. B is going to equal C comma infinity intersect E. I don't know, what should C be? C will be orange. I haven't used orange much in this screencast. So B is going to be all this green stuff over here. Well, look, in A, the most amount of stuff I could have is negative infinity to C, right? And I'm going to actually take less of it because I'm only going to take the stuff that's in E as well. But all the limit points of this are either stuff in here or C, none of which is contained in here because this contains at most open interval C to infinity. So this does not contain C, and this one has kind of the best case for B to include a limit point is that it would have to contain A. So what do I know? I know that A, the limit points of A, which are basically going to be at most negative infinity to C closed, that's going to equal the empty set. And similarly, the limit points of this intersected with A are going to have to be the empty set. Which means that these two are separated sets. So, if E is equal to all the stuff in E that's to the left of C and all the stuff in E to the left of B, implies, so if E were to be equal to the union of these two sets, that would mean that E is disconnected. Why? Because E would be the union of two separated sets. And that's the definition of disconnected. But that's a contradiction because we're assuming that E is connected. So that's a contradiction. So E is not equal to A union B. And how could it not be? Well, it includes, A union B includes everything to the left of C and everything to the right of C. So the only possible thing is that E must be equal A union B union C, because that's the only possible thing missing. So C belongs to E, which is exactly what we want to prove. It's supposed to be a check mark. Okay, now for the other direction, I'm going to assume that whenever I'm going to assume that E is an interval. That's really what this is saying up here. So if I assume that E is an interval, I'm going to prove that's connected. And the way I'm going to do that is I'm going to come up with a sequence such that this thing is contained in A and X belongs to B, or vice versa. So that's the basic setup. And that is a theorem. A theorem from the textbook says that whenever this happens, whenever you have a sequence that's completely contained in one of them converges to a point in the other, or vice versa, that means that's going to be connected. That's going to be enough to show that we're done. So I'm going to split this into two different parts. So the proof will conclude in the next podcast.